a planet so extreme most scientists said it couldn't possibly exist. Yet in 2008, astronomers detected WASP-12b, a gas giant orbiting its star so closely it completes a year in just over 1 day. According to every planetary formation model, it should have been destroyed long ago, ripped apart by gravity, and seared by heat hotter than molten steel. Its atmosphere is streaming away, its orbit shrinking by the hour, and nobody can quite explain why it's still here. How did the laws of physics get broken, right in front of our telescopes? If a world like this defies everything we thought we knew, what else is hiding out there, waiting to rewrite the rules? The first sign was a dip, barely a fraction of a percent, in the brightness of a distant star. On a chilly night in 2008, the Super WASP array recorded a subtle, repeating signal from a patch of sky in Auriga, Auriga. The pattern looked familiar, a planet passing in front of its star, blocking just enough light to trigger the automated alert. But the numbers didn't add up. The interval between dips was only 1.09 days, far shorter than most known exoplanets. The depth and shape of the light curve suggested something massive, much larger than Earth, with a shadow that lingered just over 3 hours each time. In the control rooms and on late-night message threads, doubts piled up. Could the photometer have glitched? Was it a software artifact, a cosmic ray, a misbehaving pixel? Super WASP's detectors were notorious for their quirks: temperature shifts, electronic noise, the occasional ghost signal from a bright star just outside the field of view. Analysts combed through calibration files, checked reference stars, and ran the pipeline again. The anomaly persisted. One graduate student, running a custom code patch, flagged the orbital period as an outlier. Senior astronomers pored over the raw data, arguing over whether the signal was real or just another false positive in a sea of noise. As the hours ticked by, the debate intensified. If the data held up, this was no ordinary planet, but confirmation would require more than a flicker on a screen. For now, all anyone had was a fragile pattern of starlight, and a mystery that refused to fade. Confirmation didn't come with a single eureka moment. Instead, it unfolded through a gauntlet of double checks and late-night cross-checks. The first step, independent teams at 2 other observatories locked their telescopes onto the same star. Their data matched the original Super WASP signal. Same 1.09-day rhythm, same 3-hour dip every cycle. Timing checks lined up so tightly that even the most skeptical astronomers started to take notice. Peer review brought a new round of scrutiny. Raw light curves, calibration logs, and code outputs zipped across continents. A graduate student in Cambridge, running a custom script, flagged the orbital period down to the 4th decimal place. The numbers held. At the Harvard-Smithsonian Center, a lead astronomer compared the transit times against archival data stretching back years. No sign of a false alarm. Every facility, every method, pointed to the same answer. This was a planet, and its orbit was impossibly short. Overnight, the debate inside the research teams shifted. No one could explain how such a massive world could circle its star so tightly and survive. The certainty was now mathematical, not just anecdotal, a planet locked into a death-defying dance, rewriting the boundaries of what a solar system could be. The question was no longer if the planet existed, but how it could possibly last another year, let alone another million. At just 0.023 astronomical units from its star, less than 1/10 the distance of Mercury from our Sun, WASP-12b circles through an environment few scientists imagined a planet could survive. The numbers are punishing. Daytime temperatures soar above 2,500 Kelvin, hot enough to vaporize aluminum and melt titanium. This is not the gentle warmth that nurtures life on Earth. It's a relentless blast furnace, driven by a star shining over 100 times more fiercely than the Sun does on Jupiter. The planet's skies, if you could call them that, are a study in extremes. Most worlds reflect some starlight, but WASP-12b absorbs nearly all of it. Its albedo, an astronomer's measure of reflectivity, comes in at less than 0.06. That makes it darker than fresh asphalt. Instead of glinting in the cosmic spotlight, the planet radiates its heat back into space as a dull, infrared glow. Its day side is a sea of superheated hydrogen, carbon monoxide, and metallic vapor. Night never really falls here. The planet is tidally locked, one hemisphere always facing its star, the other trapped in perpetual shadow. But even on the dark side, heat seeps through the thick atmosphere, carried by winds faster than any hurricane on Earth. The result is a world with almost no true night, only gradients of blistering heat and dim, ember-like twilight. At this distance, the rules of planetary physics begin to break down. Gas giants are supposed to cool and shrink over time, but WASP-12b is swollen, its atmosphere puffed up by the constant onslaught of stellar radiation. Astronomers call this hot Jupiter inflation, a phenomenon so extreme here that the planet's radius stretches to nearly twice that of Jupiter, even though its mass is only a little greater. The line between planet and star starts to blur, a world teetering on the edge of destruction, held together by gravity and heat and nothing else. Gravity does not simply hold WASP-12b in place, it stretches the planet to its breaking point. Locked in a desperate tug-of-war with its star, the planet's outer layers bulge outward, distorting into an egg-like shape. This is tidal locking, but taken to an extreme. Instead of a neat, round world, WASP-12b is drawn so close that its atmosphere swells right up to the edge of what physicists call the Roche lobe, the invisible boundary where the star's gravity begins to win. Cross that line and material is lost forever. Spectroscopists have found the fingerprints of this ongoing destruction. In the ultraviolet, telescopes detect magnesium and iron streaming away from the planet, their spectral lines smeared and shifted by high-speed outflows. Hydrogen forms a vast envelope, so large it sometimes blocks extra starlight before and after the main transit. This isn't a gentle leak. The planet is bleeding off billions of tons of gas every second, forming a tail that may wrap around the star itself. The process is relentless. Each orbit strips away more of the planet's mass, tightening the spiral toward disaster. The very act of orbiting so close feeds the loss, as tidal forces stretch and heat the atmosphere until molecules break free. The evidence is written in the light, escaping metals, swollen silhouettes, and a clock ticking down. For scientists peering through spectrographs, WASP-12b is not just a survivor, it's a planet caught in the act of being unmade. Transit timing teams around the world started clocking every pass of WASP-12b with relentless precision. The numbers told a story no one wanted to believe. Each year, the planet's orbit shrinks by about 29 milliseconds, an amount so tiny it's almost lost in the noise, but relentless all the same. Over a decade of data, the trend holds steady. The planet is spiraling inward, its path tightening with every lap. Models project a grim countdown. At this rate, WASP-12b has only a few million years left before it's swallowed whole. For the scientists watching the data stream in, the sense of urgency is real. Every new measurement hammers home the same message. This is a death spiral, visible in real time, and the clock is running out. WASP-12b isn't an isolated oddity. Its existence sends shockwaves through the field of exoplanet science, forcing a reckoning with every model of planetary formation. The James Webb Space Telescope has turned up spectral fingerprints in other worlds, chemical signatures that don't fit any familiar recipe. LHS 3154b, for example, is a planet so massive compared to its tiny red dwarf host that the math simply doesn't work. Theories that once set clear boundaries now crumble under the weight of new data. Astrophysicists debate in conference halls and late-night calls, wrestling with equations that refuse to balance. Each new, impossible planet widens the search for life, hinting that the universe may be far more chaotic and far less predictable than anyone dared imagine. In 2008, astronomers using the transit method confirmed WASP-12b, a planet orbiting its star in just 1.09 days at a distance of 0.023 astronomical units. Its surface temperature exceeds 2,500 Kelvin, and its atmosphere is being stripped away, with magnesium and iron detected escaping into space. Observations show WASP-12b's orbit is shrinking by 29 milliseconds each year, giving it only a few million years before destruction. Despite decades of research, current models cannot fully explain how such a planet formed or survived so close to its star. Other planets like LHS 3154b and HD 189333b also defy established theories. As of today, scientists have revised planetary formation models, but many questions about migration, composition, and fate remain unresolved. The existence of WASP-12b proves that our understanding of the universe is incomplete, and that the search for new rules has only just begun.